Hello, in this video we're going to take our first look at simple machines, a topic that tends to not be covered in schools. Now here I'm going to give the usual introduction. This is going to be an overview to simple machines, what they are, how we go about analysing them, and then I'll do subsequent videos looking in more detail at each individual machine. So what's going on here? Well, we're taking a step into engineering. This is moving away from pure physics as we've been doing so far, where in pure physics, as you remember, we observe the world, we make observations, and then based on those observations we create descriptions about how the world works. Now engineering is different. We're then using those descriptions in order to get more desirable outcomes in the world. So we're not creating descriptions in engineering, we're using our knowledge of physics to our advantage. So we're being clever and we're building machines in this case that are going to usually allow us to lift up heavier objects. That's the first thing that we're going to be looking at with these simple machines. So what does simple machine actually mean as a term? Well, the simple just means we've got a single mechanism. So we're looking at the building blocks of more complicated machines here. What are the mechanisms that we can use to create machines? And a machine in this context means something that takes an input force and then creates an output force with a different magnitude and or different direction. So that's what we're trying to do here. So if you think of trying to lift up a heavy object, we might not be able to lift up an object. We got something which is just too heavy for us sitting on the floor. We're applying some force here, but it won't shift. We can then put a machine in this where actually we can apply that same force to our machine, whatever that may be, which then creates a larger force. That machine will then apply a larger force to an object. And that larger force may be in a different direction and it will get the object to move. So it's all about changing the magnitude of these forces. So that's our input force, which is small, to a large output force, potentially in a different direction. And now, lo and behold, our object starts moving, which we couldn't shift before. So what are these simple machines? Right, well, traditionally, there are 6 of them. And this goes back to the ancient Greeks. Archimedes, surprise, surprise, the godfather of engineering, he was playing around with all of these. He had 6 simple machines that he was dealing with all the time. And these are still the ones, these are still the 6 that people look at as our basic building blocks of more complicated machines. And you'll be familiar with a lot of these. You've got an inclined plane, that's just a slope. It's easier to push an object up a slope than it is to just lift it straight up in the air. So that's the operation of an inclined plane. Levers you'll be familiar with, we would have done at school. You think something like a crowbar, you've got a pivot point, you always have to have a pivot with a lever. You want to prise something open, you stick the one end in which is close to the pivot, you apply a force at the other end, and lo and behold, you get a big force that pops the box open or whatever you couldn't open with your bare hands. So that's the principle of at least one type of lever. Pulleys are where we're using ropes and magnifying the force on those. So you've got one rope that will be wrapping around these pulley systems. So you wrap the rope around. Here we're pulling down with one amount of force. So you think of how ropes work. We've done loads of stuff with tension, and that tension is transmitted throughout the length of the rope. So now we've got 2 lots of tension pulling up over here. So we've doubled the lifting force to some weight that's hanging off the bottom of the pulley. Using ropes in pulleys, wheels and axles. So for stuff that we're spinning round, you might have a big wheel with a crank handle on it. You turn the big wheel round, you've got a little axle. The axle on the wheel is going round at the same speed, but we're now going to get a greater force being applied radially on this axle. because it's well, it's closer to the center of rotation. So okay, the direction is staying the same here, but we're still multiplying the force up. I mean, you could with this go in the opposite direction and apply the force to the axle, and then have a smaller force on the wheel. So you can go in either direction, but usually you're going to go the other way around. So that's wheel and axle. Screw, you've got some screw head. The screw go with the thread on it is going into a wall, so we're turning the screw around, rotational motion, and the thread is then driving the screw into the wall. So we've got a definite change of direction there, and of course we can change the magnitude of the force as well, depending on the design of the screw. You know, how the thread is set up and the size of the screw head. And the last one here, the wedge, which is the one that's always annoying for actually getting problems to analyze, because the forces are much more difficult to quantify than they are in the other 5. So a wedge, you could think of, classic example is an axe. So the axe head, if you think of that axe being driven into a tree, so we're swinging it in this direction, it hits the tree, we're now splitting the tree. I mean, I know with an axe you're trimming off bits of material as well, you're actually shaving it off to create a hole, but the wedge principle is that we're changing the direction of those forces there, and depending on the shape of the wedge, you know, the geometric properties of it, we're changing the magnitude of the force as well. So that's a very brief overview of those 6. Like I say, well, I'll be going into all of these in more detail in subsequent videos. But you can see we're doing all the same things going on here. And you'll notice that I would have described certainly 5 of these, with a possible exception of the pulley, in very geometric terms. You can see a lot of triangles coming out here. We've got a triangle here on this slope. We've got triangles here on this lever. We've got triangles on the wedge. And then we've got these circles going on with the screw and the wheel and axle. And that leads us into our basic principles of how we're analysing these simple machines. So the first thing, there's 4 things that we're looking at here for analysing simple machines. So the first one is based on the conservation of energy principle. So we've got work in is work out for an ideal machine. So I've been saying a lot about this input force and output force, but of course we have to consider the distance through which those forces are applied, because force times distance is our work, that's our energy transferred. So the work in must be the work out. So if we've got our, let's go back to the lever example very briefly here, because we're familiar with levers. If we've applied a smaller force at one end of the lever, but we're applying that through a large distance, so we've got a little force, small f, through a big distance, capital D, and we're now moving the other end through a much smaller distance, little d, so we get a much bigger force for an ideal machine where we've got no losses going on. I mean, there are always going to be losses, but for an idealized machine, we've now multiplied up the force, but we've reduced the distance that force is applied through. So that is work in is work out. This is conservation of energy. So that is always going to be something that we want to be looking at. Now we've got the comparison between our forces and our distances, which give us our next 2 descriptions. We've got the mechanical advantage. So mechanical advantage, so abbreviated to MA, that is our output force. So in this case, capital F is our output force divided by our input force, small f. So it's what multiple of our input force have we ended up with? You know, how much have we multiplied the force up by? So if our output force is 10 times the input force, then we've got a mechanical advantage of 10. So a fairly simple thing to work out there. Then we've got velocity ratio, which is really looking at the distances that things are moving through here, even though it's called velocity ratio. But you think, well, if they're moving through different distances, it's in the same amount of time. So whether you say distance ratio or velocity ratio, it doesn't really matter if you've included time in there, because the time that we're applying the input force is exactly the same as the time we're applying the output force, because these things are tied together in the same machine. So velocity ratio could be called distance ratio. It doesn't really matter. Just one of them is including time and one of them isn't. So the velocity ratio is now just looking at these distances. So our velocity ratio, VR, this time they put it the other way round because they want to keep numbers greater than 1 by and large. So we've got the input distance divided by the output distance. So if we've got a mechanical advantage of 10 in an idealized machine, we're also going to have a velocity ratio of 10. Because if we do the little f times the big D is going to be the same as the big F times the little d. These things have to match up because that is our work in, work out. F times D is equal to F times D. So we're just rearranging those, really, these forces here, this equation. If you think we're rearranging this equation to say, well, D over D equals F over F, that's just a rearranging of our work in, work out equation. Okay, so that's our velocity ratio. And then we've got our efficiency. So we're not going to, in the real world, have ideal machines. We can draw out our designs for machines and design them and analyze them as if they're ideal. But one of the good things about when you actually go into the world with a simple machine is forces and distances are usually things that we can measure fairly easily. Okay, we have got the exception of the aforementioned wedge, which can be a bit of a pain. But we can measure efficiency of these machines quite well, because these are just, stuff. We get some force meters out, we get some rulers out, and we calculate these things. So if we're doing our efficiency on this, so efficiency is the work out divided by the work in. So that is F times D over F times D, getting the uppercase F times lowercase d. Well, looking at that for our mechanical advantage and our velocity ratio, that is the mechanical advantage divided by the velocity ratio. So that's two different ways of writing out our efficiency equation. And these are the descriptors that we're going to be using time and time again when we're analysing these machines. So the last thing that I'm going to say in this video is just to take a very quick illustration here of coming back to this lever again, because we have got these geometric principles that come up again and again and again, and a lot of our analysis is going to be geometrical in this. So we push down on one end of our lever with force little f, it comes up at the other end with a bigger force of big F. Now we can set up here that if we're not moving that far, we've more or less got similar triangles going on here. We're going to go through a greater distance here and a smaller distance there. But because these angles are all the same in both triangles, you can see we've got similar triangles here. So our analysis of our mechanical advantage and our velocity ratio, when we're just drawing out this lever on a piece of paper, we don't need to measure these forces and such like in order to get our mechanical advantage. We can just look at all of these ratios of distance. So our velocity ratio, d over d, well, that's also easier to measure along the hypotenuse of these triangles. So we can measure the distances from the pivot point because they're going to be in the same ratio because these are similar triangles. So if we were going to call those, I don't know, X and Y, then we can just say that is exactly the same as x over y. So we've taken a step away from immediately looking at distances moved and forces applied to starting to look at the geometric setup of the system. I mean, in fact, in this case, I mean, I was saying if we're not moving all that far, but even if you've got an arc going around here and you're thinking of it as moving in arcs of circles, these are still going to be similar. We're still going to be able to compare the distance from the pivot point. So we're still coming back to these geometric properties. And this is what we're going to look at in the setup of all of these simple machines. And that's what I'm going to put in these subsequent videos. We're going to analyze each one of these machines and then look at some specific problems. But that's given a brief overview. The main thing to remember from all of this is our methods of analysis. These main terms here: mechanical advantage, velocity ratio, efficiency, and our conservation of energy.